So, next speaker, Professor Sergey Antonyan. Some new equivariant properties of Milnor construction. Please.
Announced that they are in Kiev, but I feel myself in Odessa. Thank you for invitation and for attending this talk. So I'm going to try to cover the following topics. So free G spaces, principal, G fibration, Milnor construction. Okay, some other properties here listed. Okay, let's go ahead. So free G space is a G space. So first, G space is a topological space indirect with an action of a given group. An action is a continuous map from this Cartesian product to X such that so the unit element of the group is acting like an identical homeomorphism, and then a product of two elements in the group is acting like a composition of two maps, in fact, two homeomorphisms. So this is well known. So such as spaces endowed with the action of group are called G spaces. Now, in my talk, we are mostly interested in free G spaces. A minute, I will define what means free. First, a continuous map is called a G map or an equivariant map if it commutes with the given actions in X and Y, respectively. Okay, for a point in a G space, a stabilizer is defined to be the set of all elements in G which fix this element. So this is Gx, this is a subgroup of X, and it is trivial to observe that under a equivariant map, so the stabilizer can be only enlarged. So Gx is a subgroup of G sub Fx. So the action is called free if the stabilizer of every point is the trivial subgroup of G. In other words, every non-trivial element of the group moves every point of the space. So such kind of actions are called free. Also, we have the notion of an orbit. Orbit of a point is the set of all Gx, and the set of all orbits is denoted in this way, and always we consider the quotient map in here. And then we have the orbit map, which sends a point to its orbit. So this is the orbit map. So principal G fibration is one of the principal notions in algebraic topology. It is defined in this way. It is a subset of the Cartesian product X by X, which consists of all points X, Gx, of all pairs which belong to the same orbit. So this is X star. If we have a point in X star, then always there is an element tau from G which sends X to X prime. So in other words, tau is well defined. We have a well-defined map from X star to G tau, and evidently it satisfies the following properties. Tau XX is the identity. So here we have this transitive property, and we have this symmetry property. So following to Huesmüller, if this translation map is continuous, then a free G space is called principal. In this case, the orbit projection is called the principal G fibration. So here are quick examples. If our group is two-element group, cyclic group, and the X is the sphere, then we have the antipodal action here. And in this case, X star consists of all the pairs x minus x, and the translation map evidently is continuous because it is equal plus or minus 1, and the principal G vibration in this case is orbit map from the sphere to the to the real projective space. Another quick example is when X is a subgroup of X, G is a subgroup of X, where X is a topological group, and the action is given by a multiplication, usual group multiplication. Then X prime consists of all pairs for which Yx minus 1 belong to G. And the translation map is just this one. And evidently this map is continuous. So we have a principal G vibration here. Okay. Now, another examples are non-trivial. They are based on classical results. The first one is by Gleason from 50s, early 50s. It claims that if G is a compact Lie group and X is a free G space, then the orbit map is a principal G vibration. And this result in early 60s, 10 years later, was generalized by Richard Palais, which exactly claims the same to be true for Lie group actions, proper Lie group actions, not necessarily compact, any Lie group, but the action is required to be proper. In a minute, I will define what means a proper action. So in this case, again, the orbit map is a principal G vibration. Now let me go to the main topic in my talk. What is a Milnor construction? Milnor construction is a principal G fiber constructed by Milnor for arbitrary group, not necessarily for arbitrary topological group. So this is the following one. Consider the group G, topological group. Here, I is the unit interval, 0, 1, okay? Consider the countable power, countable Cartesian power of this product. And then an element from here is just a sequence. T1, G1, where T is a number, G is an element of G, T2, G2, and so on. Infinite numbers, sequences. But such that almost all numerical coordinates here are zeros, and the sum of them is 1. So we consider only such sequences. Okay, this is our new set. Then we define an identification on this set. So two sequences we call equivalent if they have identical numerical coordinates. T I is equal T prime I for all E. And whenever numerical coordinate is non-zero, then also we require that the group coordinates also are equal. Okay, this is the identification. And in this case, instead of this sequence, we write the sum in form of sum, because due to this identification, if sum TE is 0, then we can cancel this term. Okay, then we have projections from EG. EG is just the set of these identification classes. So we have TE, which maps this element to the coordinate TE. And when the TE coordinate is non-zero, also we have a projection to G. Here, this is going to GE, okay? When the TE is non-zero, then the other coordinate is well-defined. So so we know this set So these projections we consider to endow this set, e.g., with the smallest topology that makes all these maps continuous. This is the definition of the topology on this set. Okay, so together with this topology, e.g. is called Milnor construction, or Milnor space in this case. So now we start the equivariant part. There is a natural action of the group G on EG defined in this way. Coordinate by coordinate. Here is multiplication, G by G1, G by G2, and so on. This is the action. So it was a locally trivial principal vibration is the following. Here is the definition. So each point in the orbit space should have a neighborhood U such that the inverse image P minus 1 of U is like a Cartesian product, but equivariantly. This is G equivalent to the Cartesian product in the following sense. Look here. Here we have an action of the group on the first coordinate, on the second we don't have. Here we have the action originally given, then we have this commutative diagram. So if the diagram commutes, then we call this locally trivial principal G vibration. Okay, this is also a well-known notion. Okay, from Gleason's theorem, it follows that the orbit map in the compact Lie group case is locally trivial principal G vibration. And the same was generalized by Palais, is true for any Lie group action, free Lie group action. So the projections are locally trivial or locally trivial principal G vibration. Okay, this is in fact all known results. Now, Milnor also proved that EG is contractible, so topologically, homotopically trivial space, and also proved that any two equivariant maps from X to EG are G homotopic. So these, in fact, are non-trivial results, but they are classic results. And for any topological group, the orbit map, so the orbit space is called in this way, is called the classifying space, is principal G vibration for any group. So these are classical results. So in my talk, I'm going to give another description, a little bit different description of the Milnor space, Milnor construction, and show some equivariant properties. So now I will omit recalling you another universality properties of Milnor construction. These are well known. You can see, for example, in Milnor or Hughes-Milnor book. So I will omit this and go to the alternative construction of Milnor's construction. So let's consider the cone. If we have a topological space, consider the cone. A cone is the quotient space of the cylinder where we identify the bottom of the cone to a point. And then the resulting space, as a resulting set, is denoted by cone X. But here, in a difference of the classical case, I'm going to consider different topology. So quotient topology is good when X is a compact space, but when X is not a compact space, or in my case is interesting when X is a traceable space, but not compact, then we will consider another topology. So this topology is defined in this way. Recall that a subset in the cone containing the vertex belongs to the weak topology if the pre-image is open and So this is a new different, and there is an epsilon such that the strip 0 epsilon by x is still contained in this preimage pi minus 1 u. So this automatically is fulfilled when x is compact, but when x is not compact, this is not an automatic issue. We require here in a definition. Okay, if u does not contain the vertex, then it is called open in the weak topology if just the preimage of u is open. This is the weak topology. We consider the con with this topology. Now, in the equivariant case, when X is a G space, then there is a canonically defined action level by level of the group on the cone. Okay, here you see a small picture of the cone. So in this case, when X is metrizable, the cone also is metrizable, and here is a proposition, even a formula for a metric on the cone we can write down. If X is metric space with such kind of metric, then this formula, you see here a formula, defines a metric on the cone, which exactly define the weak topology on the cone. So this D star is less than or equal to square root of 2, and this star is complete whenever D is solved. So now going back to the Milnor's construction, let me recall you the join. So we have a countable number of topological spaces, then we consider the cones over these spaces, and then I consider the countable product of these cones, okay? Every cone is already a topological space, so countable space product is also a topological space. And here, inside of this Cartesian product, we consider all sequences for which the sum of the numerical coordinates is 1. So then this is a join, the join as a set at this moment. So in our case, the interesting case is when all these X are G, and the G is a topological group. In this case, we shorten the denotation in this way, J sub infinity of G. And the natural multiplication on G defines an action here. Then J sub infinity becomes a free G space. Okay. It turns out that the Milnor's construction is G homeomorphic to this one. This is a little bit, gives us a little bit more transparent, as I think, description of Milnor construction. Why? Because the cones are simple things here. So we can consider the product of the cones and the join. This join is just a subset here with the induced topology. That's it. So the Milnor's topology coincides with this topology. This is claiming in the theorem. Moreover, this homeomorphism is equivariant. But in fact, the homeomorphism is the formula for the homeomorphism is obvious.
Excuse me, sir, could I ask you something?
Yes.
Okay, so about this theorem, this works for any group G, or there is some restriction on group G?
Yes, this works for any group G.
So even if G is discrete, yeah?
Yes, exactly.
Okay, thanks.
Exactly. So the formula for homeomorphism is this, and then the proof consists in verifying that this is in fact homeomorphism, and it is evident that equivariant homeomorphism. So I consider this a little bit more transparent than the original Milnor's construction, but this I did because I was interested in equivariant properties of EG, which were not considered in the literature up to my best knowledge. So now let's go to this direction. So for example, the metrizability of EG in Milnor's case is not an immediate task to prove that when G is metrizable, then EG is also metrizable. But here is almost trivial, because if G is metrizable, now the cone is metrizable, the product is metrizable, and due to the theorem, so the topology here, the original Milnor topology, is the same induced here. That's why it is metrizable. Now about equivariant properties. The questions are the following. Is the Milnor construction G equivariant absolute extensor or not? Or G equivariant neighborhood extensor or not? So similar questions for the classifying space, for the orbit space. And finally, in algebraic topology, never people was interested what are the topological structure of EG and by G topologically. Can we identify these spaces? Okay, let's go ahead to this direction. And here I'm going to explain what means equivariant absolute extensor and so on, all these notions. Here is a small dictionary. Let K be a class of topological spaces, then we will denote by GK the class of G spaces such that X as a topological space belongs to K. For example, GM is a metrizable G space, or G for compact spaces, G compact space, and so on. Okay, now absolute extensor is the following thing. Suppose we have a G space from some class, K. Here F stands for free. We will consider only free actions. Okay, K is a topological class. F means that the actions are free. So this the notation is for free. For such kind of spaces, if for any free G space from this class and any closed subset, invariant subset of Z, any equivariant map from A to X admits an equivariant extension to the whole space. So in this case, we call that this space X is G absolute extensor for the class GK for free actions. In our case, we are interested in paracompact free property spaces and metrizable free property spaces. Okay, these two spaces.
You have 3 minutes.
Our first result is that when G is a locally compact group, then the natural action of G on the Milnor's construction is a proper action. So now let me explain what means a proper action. Sorry, I go back. I need to go. So what means a proper space? I will explain this in a minute. And the next result is the following, that when G is a Lie group, then the Milnor construction is G equivariant absolute extensor for metrizable free G spaces, and similar result without equivariant for the orbit space. Okay, now what's the proper action? So in short words, proper action is an action of a locally compact group, which is similar to the actions of compact groups. Now, more precisely, following tuple, let's call a subset in a G space small if for every point in X there is a neighborhood V such that this set, which consists from all those elements of G such that the transition or translation by G of S meets F. So if this set is not big in the sense that it has compact closure in G, okay? In this case, S is called a small set. Then a G space is called proper, or the action is called proper, if every point in the G space admits a small neighborhood. Of course, when the acting group is compact, then the action is always proper because this set has compact closure in G because G is compact. Okay, everything has compact closure. But if G is not compact, then this makes sense. So introducing this notion, Palais was able to translate from the compact case many results to the case of proper actions. Now we are going in this direction. So here is, so in the case of G discrete, this was known like a properly discontinuous actions. In dynamical systems, this notion is also was known under another name of dispersive dynamical systems. Okay.
That is all. Excuse me. You have 2 minutes.
Finish?
2 minutes.
Okay, if you have questions, please ask me now.
Excuse me. How to use your result in theory of the knots?
Excuse me.
Because Milnor map meet in theory of knots. Yes?
Excuse me, could you repeat one more? What is the question?
My question is, how to use this result about Milnor map in theory of knots?
Ah, okay. So this is good question. Yeah, it is good question, but I have not worked about that. So my short answer is,
okay.
I don't know. Mainly, I'm interested in equivariant properties, but this was just recently started. So maybe there is, I think, a big field to see for applications of these results.
Yes, okay.
So unfortunately, so maybe if I have there is another generalization introduced by your compatriot, but Taras Banach, for another kind of Milnor kind of construction. And also I had some results about this new construction, which in a difference of Milnor construction is complete. These EY tilde spaces are complete, but the meaning is quite similar, but interesting construction. Just these 2 words. Thank you. So more questions. I am ready to listen.
Okay, so could I ask something?
Yes.
Yeah. Okay. So if I have two comments and some question. If you have 2 topological spaces, then you can define in the well-known way they join. But also you can define the join of 2 spaces using the construction by Kohn. How you do this, and you can show that on the level of the join of 2 spaces, both constructions are not the same. But you claim that if you take your construction, then there's no restriction on group G. So okay, so I don't know what
please pay attention that when I say Kohn, this is not with the question topology. That's right. The topology is weak topology.
Weak topology.
Weak topology. Yeah.
So maybe that is helpful.
Yeah. In your question, what X base spaces are compact. So what constructions are?
Yeah. Okay. So for me, so that's the point. Thank you very much.
Okay.
Yeah. Okay. Great. Okay. And now is another question. So, did you publish these results somewhere?
Some of these results, yes, are published.
So is this paper you just see one universal property spaces? I know, and this one.
Not this paper. Yeah, it was published 2 years ago. Some of these results were published 2 years ago in topology and applications, but not this paper you see here, because this is old paper. But are published, some of them, in topology applications.
Okay, but the context of of your talk is not published yet. That is something new.
There is something new, yeah.
Okay, so could you send me, please? Maybe you have the files. I'd be happy if you send me it.
Okay, Marek. Your email, I think it should be in my computer, but if not, please recall me. Okay.
Okay. I have down new email address. You can find my email address in the abstract, which you can see on the site of conference.
Okay. Thank you, Marek.
Okay, and the last question, if I can ask, that there is a generalization of Milnor construction if the group G replace by what is called a infinity space, that is the Stashev construction.
Yeah.
And how do you think is also your construction could be made for a infinity spaces?
Yeah.
The a infinity space is some generalization of 8 space.
Yes. So just my answer positive is intuitive. I have not tried. This is another very good question, very interesting thing to try. So my feeling is that yes, it will work.
Okay, thank you very much. So please remember sending me the file. I will be very, very happy. Yeah.
Okay, thank you for your interest, Marek. Yes.
Okay, well, thank you very much. Very, very nice. I enjoyed very much your talk.
Thank you.
No, that is all. Thank you.
For me, it's all. Yeah.
Thank you for your report.